Welcome back. Now we're going to talk about absolute extreme values on a closed bounded region. And I've drawn a curve on an XY plane here. Looking at this curve, we can see there's a relative extrema at x equals 0 and maybe a relative extrema somewhere in here. Let's just call that x equals 6. But if I were to say, well, tell me the absolute extrema, we would have to look at it on a closed interval. So whenever you're doing a problem with absolute extrema, you're given a closed region. So maybe I say only consider this function from 2 to 8. That's my closed interval. So that means I have this curve that looks like this. And so now, because I have bounded this region, I've put it on a closed interval, it's no longer a finite function. It doesn't go down to infinity forever. We don't know what goes on over here. We're saying, hey, we're just looking at this piece. And there can only be one absolutely highest point on that region. So in this case, the absolute max would occur at x equals 6. So it's very similar for multivariate functions. We just also have to consider points that are on the boundaries as well as those critical points. So if you remember going back to Calc 1, when you were finding absolute extrema, you would not just look at that point and this point, but you'd say, hey, I got to check over here on these boundaries because that could represent a maximum value. If I had changed this and had this go to, say, 0, then that would mean this function would go over here, and that absolute max would be right on that boundary. That would be the highest point. All right, so let's look at an example here. For this example, we're going to find absolute maximum and an absolute minimum value for the function. One thing to note, if we're talking about absolute max and absolute min, there will always be a absolute max and an absolute minimum because we've closed the region. Okay, so we've got a closed bounded region, there's a boundary, and even if we couldn't have found a local max or min, that absolute max or min would potentially occur on the boundary. So in this case, my multivariable function, 2 plus 2x plus 4y minus x squared minus y squared, is bounded on a triangular region by x equals 0, y equals 0, and y equals 9 minus x. So the first thing we are going to do here is visualize that triangular region. So it's in quadrant 1, and then we've got this diagonal line. So we've got this point here, I'll call this B, 0, 9. Call this guy A, 9, 0, and then we have our origin O. So the surface, this is representing, we have some surface and it's passing through this triangular invisible plane region. And so we're looking at just the part of the surface that's falling inside this triangular region. And we want to know where the maximum and minimum values occur. So that was my first step, was to draw my picture. Think about my space. So the second thing I'm going to do is I need those partial derivatives. So partial with respect to x gives me 2 minus 2x, and partial with respect to y gives me 4 minus 2y. At this point, we solve each of these equal to 0. So that first one, I'm going to get x equals 1, and my partial with respect to y, I get that y equals 2. So this leads only one critical point. Now, keep in mind, this could be solving a system of equations, and we could get 2 x values that we have to plug in and find 2 corresponding y values. We're getting one critical point. So there is one critical point on the region. And that critical point is the ordered pair 1, 2. 1, 2 is right about in there somewhere, not drawn to scale. But you could end up with a situation where there is no critical number in the region, and then we just go talking about what's occurring on these boundaries on the edges of my region. So we've got one critical point, and we can find the function value for that critical point. If I put 1, 2 in there, I know that f of 1, 2, evaluating that gives me 7 as my function value. All right, so the next step after we found those critical values, or the critical point on the region, is third, we're going to consider boundary points. So points on the boundary, on the edge of that region, on the endpoints of the closed interval if we were thinking about Calc 1. And in this situation, we're going to deal with 3 cases because we have 3 boundaries. We have y equals 0, x equals 0, and then this line, y equals 9 minus x. So the first thing we will do will be to consider what's going on the horizontal base boundary there. We've got y equals 0, or rather the segment OA. So if we go back and we think about our function f of x, y, if I let my y value equal 0, letting y equal to 0, I'm going to zero out some terms, and I'm going to end up with just the function 2 plus 2x minus x squared. So I just pulled my function in from before. So this segment OA, this only exists for x values that are between 0 and 9. That's my domain. So we have to look at the endpoints. So if I let x be 0, and of course y is already 0, I get out the ordered pair, or the value 2. And if I let x be 9, y was already 0, and I plug that 9 in, I get out negative 61. So at the origin, my output, or my z value, is 2. And over here at A, my output, or z value, is negative 61. So I also need to look and see if there are any critical points that occur on this boundary. And since I have plugged in 0 for y, I have just turned this into a function of x, which we can differentiate normally. So f prime of x, 0, that gives me a derivative 2 minus 2x. Solving the derivative equal to 0, because that's where my critical values come from, I'm going to end up with x equals 1. So that means we also have the point when x is 1 and y is 0. And if I take that 1 and plug that, again, back into my original function, the output I get there is 3. So far, we have 3 points that we need to consider in our absolute maximum or minimum list section. If we include this critical point that is inside the region, we have 4. So we've got to keep going. We need to consider the boundary from OB as well as the boundary AB. So I've refreshed our screen. We still have our function, and we've got our region. These are the 4 points we just talked about that we found that could represent an absolute max or an absolute minimum. So part B, we first looked at the boundary OA. Now let's look at the boundary OB. And so what's going on there? That is where x is equal to 0. That's my segment OB. So if x is equal to 0, then we take that function, f of xy, and that's 0y. And what does that do up here? That zeroes out these x's and this x, which leaves me with 2 plus 4y minus y squared. So notice now f is a function of a single variable, y. So keep in mind, this guy has the same domain, the same domain. Those y values only exist between 0 and 9. Now, we already looked at 0, 0, so I don't need to plug that in. I've already got that value here. But I do need to look at this endpoint B, which is the ordered pair 0, 9. So f of 0, 9, if I plug that in to my original function, my 0 and 9 for x and y respectively, I get out negative 43. So I've got that point. I'm going to go ahead and list that over here. I've got f of 0, 9 is negative 43. And like I said, I don't need to consider 0 because I've already considered 0, 0. So I don't need to plug in 0 for y. Now we need to see if there are any critical points on this boundary. And that involves us, again, taking the derivative. So f prime of y gives me, I should really write 0y. But that gives me 4 minus 2y. And if I solve that equal to 0, I end up with y equals 2. So now I have another ordered pair. I have the ordered pair f of 0, 2. F of 0, 2. And if I take 0 and 2, I take this 0, 2 value and plug it in up here, my output I get is 6. So I'll get that listed over here. All right, so we've looked at two boundaries, OA and OB. Now we're going to do part C, where we look at the diagonal boundary from A to B. For our third part, we're going to consider on the boundary on y equals 9 minus x, and that is on segment AB. So in that situation, my function f of xy, that's going to become f of x, comma, 9 minus x. So what I would do at this point is I would take 9 minus x and plug it in for y there, and that would give me 36 minus 4x. And I would take 9 minus x, plug it in for the second y squared. I would square 9 minus x, 81 minus 18x plus x squared, and then negate it. Simplifying all of that, I'm going to save us a little bit of work and just write it out. We get negative 43 plus 16x minus 2x squared. All right, so now I have this f is a function of x. What is the domain? The domain for this is, again, that my x values are between 0 and 9 inclusive. Now, the last two ones we had to plug in 0 and we had to plug in 9, but we already calculated 9, 0, and 0, 9. We found both of those values, so we don't have to look at the endpoints. We already calculated those. We just have to find out if there's a critical number on this boundary. So since f is now a function of one variable, f prime of x, comma, 9 minus x is 16 minus 4x. And I can solve this equal to 0. I would subtract 16, divide by negative 4, negative 16 over negative 4. I have x equals 4. So my ordered pair, 4, 9 minus 4 is going to be 5. So the function value at 4, 5, plugging that in to my original function up here, I get negative 11. All right, so I'll list that over here on the side. We have f of 4, 5 equals negative 11. So we went through a decent amount of work here to find the one critical number that fell inside the region. We looked at our endpoints, 0, 0, 9, 0, and 0, 9, 0, 0, 9, 0, 0, 9. And then we also found a critical number on each of these boundary edges. So if we want to know the absolute max and the absolute min, we just have to pick the biggest and the smallest. And my highest value, my max, is at this 7. And then my minimum, my smallest value, is at 9, 0. It's negative 61. So my ordered triple, 1, 2, 7, or 9, 0, negative 61. And because the book has so many much nicer pictures than what I can actually draw you, here are the points that we found. Here are these 7 points. We have the 3 corners. We have the one critical value inside the region, and then taking the derivative of those functions that we created by setting x equal to 0, y equal to 0, y equal to x, or 9 minus x, we were able to find these other 3 critical numbers on the boundary. And so the maximum is occurring at 1, 2, and the minimum is occurring over here at A, 9, 0. So in 3D, what we can see here, this blue being the top and the green being the underside, there's my surface, that's my function. And we said we were only going to look at pieces of this surface that were inside this triangular region. So even though what we were looking at here, even though this surface extends outside the region, we constrained it or bounded the region by using this triangular shape. And in this case, it's probably a little easier for you to see that maximum and that very low minimum value on the corner. And this concludes our video where we find absolute extrema for a surface on a bounded or a closed region. As always, send me an email if you have any questions.